morning after social event. So let us start today's heroic session. And Ivan Arzhantsev will tell us about Torus actions and trinomials.
Thank you very much. It's a pleasure and honor for me to speak at this conference. I started to work at the Department of Higher Algebra, Moscow State University. It was the year 92. In fact, very interesting time in the history of Russia. And under supervision of Ernest Borisovich. And first year, Ernest Borisovich proposed me to study unipotent group actions. It was a preprint by Lin Tan explaining recent at that time results of Steinberg concerning Hilbert's 14 problem. And it was the subject of my first talk at the seminar of Winberg and Ishik. And next year, for the next term paper, Ernest Borisovich proposed me to study reductive group actions of complexity 1. And during next years up to now, I cannot say that I studied exactly this subject. But in some sense, all my research interests are related to this type of problems, and they will also appear in this talk. So today I'm going to speak about torus actions, about Cox rings, but let me start from a completely elementary question from affine algebraic geometry. So I'm interested in affine algebraic geometry, and the subject for affine algebraic geometry is to study zero sets of polynomials in affine space. So I would like to consider a very specific polynomial, just one. Consider hypersurface, so just one equation in affine n space, and this will be trinomial. It will contain 3 terms. Here I prepared in advance because time is limited, just to not to erase this part and to fix my notation. So my polynomial consists of 3 terms, and each term depends on its individual variables. So variables are split, no common variables in different terms. So dimension is n, and this is the sum of 3 numbers, the number of variables here, here, and here. Also, I fix exponents for each term. This is the definition of my term. And I put some non-restrictive assumptions that there are no linear terms. Because if I have a linear term, then the zero set of this polynomial is just a affine space. One variable is expressible in terms of others. So I consider such a hypersurface. And I would like to ask some basic questions in affine algebraic geometry about such a hypersurface. And in fact, there were several quite recent work on this, and this is the first part of my talk. First observation. This is quite easy to check that this hypersurface is irreducible. This polynomial cannot be decomposed into product of 2 other polynomials. And my variety is always singular. One can just take partial derivatives of this polynomial and put them equal to 0, and you will find that, say, the origin is always a singular point of this hypersurface. And also, this is straightforward to check that the codimension inside of this hypersurface of the set of singular points is at least 2. So our hypersurface is smooth in codimension 1, and for hypersurfaces, this is equivalent to normality. So our variety is normal. Okay. And now to study the geometry of this hypersurface deeper, it's good to invent torus actions. So my next section will be about torus action, but in fact quasi-torus will appear. Quasi-torus action of complexity 1. For torus actions, the complexity is very easy characteristic. This is just the codimension of a generic torus. So let me put it complexity equal 1. to introduce this action, I will do the following thing. I associate with any variable in my trinomial a basis vector of some lattice. The dimension of the lattice is equal to the number of variables, so it is n. And then I put some relations on these elements. Namely, I want each monomial in this polynomial to have the same degree. I want this relation to be homogeneous. So I put the following relation, that the sum of L0j E0j equals the same for index 1 and the same for index 2. I denote this relation by star. And now I take a quotient of my lattice by sublattice generated by these relations, and what I obtain is some finitely generated abelian group. In general, this is not a lattice, it may have a torsion, and this torsion is in fact important for study of our hypersurface. And now the images of my basis vector of classes in this vector group I denote Wij, and these are elements of my group K, and they are the degrees of my variables. So I would like to consider grading of this, the algebra of regular functions on the hypersurface in such a way that this is somehow maximal possible grading under which my polynomial is homogeneous. So I consider the spectrum of the group algebra related to this finitely generated abelian group K. This is a quasi-torus. By quasi-torus, I mean a direct product of a torus and a finite abelian group, or equivalently, diagonalizable algebraic group. It acts on my hypersurface just because we put this grading on the algebra. And if I want to have a torus, then I just take the connected component of this quasi-torus. So this is indeed a gradient of complexity 1 because my variety as a hypersurface has dimension n-1, and here I put two independent relations on my lattice of rank n, so K has rank, its free part has a rank n-2. So this is indeed complexity 1 gradient. So first results claim. I will mention several papers, several results of group of people, so I listed them here, and here I just put number. This is the following one. I consider the algebra of a regular function on my hypersurface. This way it is graded by K. And the statement is that this complexity 1 gradient is factorial. Factorially graded algebra. What does it mean? It means that it is factorial on the level of homogeneous elements. So if I take any homogeneous element in this algebra, then this is decomposed in a unique way in a product of homogeneous indecomposed elements. Or, in other words, if you consider the semigroup of homogeneous elements, you forget about addition, consider only multiplication. Then this is a semigroup with a unique decomposition into products. So this is quite useful algebraic property. But you can ask when this algebra is indeed factorial, not only on the level of homogeneous element, but for any elements. And it is known, it is algebraic fact, that if you have some algebra which is graded by some finitely generated abelian group, then if this group is free, if this group is a lattice, then such graded factoriality implies usual factoriality. And in this case, especially for trinomial hypersurface, these conditions turns out to be equivalent. So my section 3 is about factoriality and the claim. Again, it can be found in the type of 1. Say that A is factorial. By factorial, I mean unique factorization domain. If and only if this K is a lattice, so there is no torsion in this quotient group. And secondly, this is some property of these exponents. This can be expressed in terms of these exponents. I will do it now. But also, one more obvious observation, that this is equivalent to the fact that my quasi-torus is connected. So this is indeed a torus. And finally, to express these conditions in terms of exponents, I introduce some numbers, di, where di is just GCD, greatest common divisor of my exponents, I1 and so on, I and I. I take one term in my relations and consider GCDs of exponents here. This is just a definition, and the condition is that this number should be pairwise cooperant. So, some class of unique factorization domains which are obtained by, we have many variants to put these exponents in such a way that this is factorial. Say example. I should write some trinomial explicitly, so I will do. If I take, I don't know, something like this, plus something like this, here 4, and say the next one is 5, and this is equal to 0, then the corresponding hypersurface is factorial.
What are the L's?
Sorry?
What are the L's? Li.
Li here, just we have 3 collections, so first collection is 3, 3. The next collection is just 1 element 4, and the last collection is just 1 element 5. So these GCDs are 3, 4, 5, and they are copering. But if I, say, replace 5 by 6, then I will have non-factorial. So in this case, it will be non-factorial.
So this looks like a generalization of Klein-Nagata or something like that, yes?
Yes, yes, exactly, very similar. Okay, next geometric question which one asked about this. Hypersurface is certainly rationality. And here, the answer is not immediate. Say it's not true that this is always rational or never rational. For me, it was an interesting task to answer this question.
I'm sorry, but in this example, do you want to specify EIJs, or is this not important? I mean, it seems that K depends on the weights, EIJ, yes?
What is EIJ? This is L. Okay, sorry, this is L. So, in this example, I have L, I have 3 groups of L.
Yes, but you somehow will specify what are the degrees, I mean, these EIJs.
You mean what are the degrees?
Yeah.
This is still alive, so this E, it was just intermediate step. Real degrees are these elements in the quotient property. So I can write down what is the degree here. So if here I have 5, then I can compute. This is very easy. So my hypersurface has dimension 3, so it will be grading by EC2. Right? And if I have 6, then it will be plus, if I'm not mistaken, something like this. Some torsion part. As a break.
I'm a bit confused about this claim because the K, you are saying that K is a lattice and K depends on your W. But your D's depend on your I's. Is it K?
Oh, I'm sorry, maybe it was better to choose better letters. So this is exponents. These are not this basis vector. These are exponents in this polynomial. So I'm sorry. So it depends only on the explicit form of my relation, not on any gradient or something like this. Okay, so rationality. Again, claim, which was distributed in several papers, but in final form in our paper 2. It says that the hypersurface Z is rational if and only if, again, some intermediate step, the divisor class group is finitely generated. In one direction, this is always the case. For rational variety, the divisor class group is always finitely generated, but not vice versa. And in this case, this is equivalent. And the condition will be the following. Again, some conditions on the exponent. Either my number D has the following form. D0 is D times something. D1 is D times something. D2 is just this something. And this something are pairwise coprime. So my first condition is that this number, only 2 of them may have non-trivial common divisors. Certainly it's up to the enumeration, this is clear. They are somehow equivalent, but only 2 of them can have common divisors. And this one, this pair, and this pair, they are coprime. Or all of them.
D to be coprime twice.
Right, D coprime to S.
Right. D is coprime. And second possibility is that all of them have 2 as a common divisor.
But the remaining are relatively prime. S0, S2, S3, 4. What about? Is it possible to have more common divisors except 2?
No. So in all other possibilities, the corresponding hypersurface is not rational. This is exactly the characterization of rational hypersurface. Either this number has 2 as a common divisor for all of them, or just 2 of them are not coprime. In particular, factorial implies rational. In general, this is not always the case, but for this type of hypersurface, this is the case. And this is just when I have this D equal 1, then all of them are pairwise coprime. And how, I will not explain the proof in detail, but how do we consider
Is
this?
it possible to express this condition in terms of the group T mod H? H mod T.
Good question. And in fact, now we almost have this answer. What does it mean, say, in sense of the class group? And this is exactly the question about how it's related to this K and H. No immediate answer. No explicit characterization, but some relations there exist. Say, one cannot say that the class group is something like a torsion in this, or no. Counterexample shows that this is not the case. How to get it? Here, torus actions are indeed important because we consider this torus acting on my Z. This is of complexity 1. So we have generic orbit of codimension 1, and I can consider the rational quotient. And rational quotient will be the curve. some C. And this curve will be always rational if I consider the factorial case, if my H is connected. But if I consider general case, then for H this is always rational, and for T this may be non-rational. And we compute the genus of this curve explicitly. And just when we put genus equals 0 for this curve, this is exactly this arithmetic condition for exponents. And by Hilbert's 90 theorem, there is an open subset which is equal to the product of my torus and some open subset of this curve. So I know, in general, the birational type of this hypersurface if I know the genus of this curve. Okay, next section will be about unipotent group actions, namely one-parameter unipotent groups. I consider additive group of my field C plus, and let me give a general definition. An algebraic variety X is rigid if there is no non-trivial J actions on X. Certainly we always have a trivial action, but if there is no non-trivial one, then we say that a variety is rigid. It's well known that J actions on a affine variety are equivalent to locally nilpotent derivations. So in the affine case, it means that the set of locally nilpotent derivations of the algebra of regular functions on X is just 0. So algebra is rigid, no locally nilpotent derivations. And here we have a characterization of rigid hypersurface of this time, but at the moment we have it under the assumption that Z is factorial, so assume Z is factorial. In fact, now we have a general case, but it's not published. This is done by Defulent, but it's not on the archive. So I formulate only under this restriction. Then Z is rigid if and only if all exponents, this is not E, this is L, are at least 2. So, in some sense, in the general case, this is rigid. And why we are interested in rigidity, there are several reasons. But one of them is that in this case, we can easily describe the automorphism group of my variety. So, next section, number 6. This is about automorphism. Certainly this is a fine variety. So automorphism group need not be finite dimensional algebraic group. It may be very big. We have examples when such hypersurfaces are flexible, so it means that the automorphism group acts infinitely transitively on the smooth locus of this hypersurface. But rigidity, this is somehow other extreme. So next plane from our paper 4. Firstly, for any variety, if X is a fine rigid variety, then the automorphism group contains a unique maximal torus. Not by conjugation, but in fact unique. So this is normal subgroup. And this gives you a lot of information about the structure of automorphous group. So you can consider, say, the centralizer of this maximal torus, take a quotient of this, and this quotient will act effectively on the torus-like automorphism, so it will be some subgroup of GL and Z. So this is indeed a strong condition. And in some other cases, under some additional assumption, say when Z is this my trinomial hypersurface for Z rigid, we can prove that the automorphism group contains the maximal torus, and in fact the maximal torus will be precisely this one, because this is a torus of codimension 1 under the action of the variety. And we cannot have an open orbit because one can check that such a hypersurface is not toric. So this is it's not toric, so this is indeed maximal. So our automorphous group is a finite extension of this torus. And this is quite easy. We have some explicit description of this finite extension in terms of the exponents here. So we have a complete description of the automorphous group under assumption that this hypersurface is rigid. And if not, then this can be huge. This automorphous. Okay, next story about such hypersurfaces, section 7. Let me consider a particular case of my trinomial hypersurfaces. In fact, when they are surfaces. And they are surfaces even only if each of this term depends only on one variable. And it has a name. So, Farm-Briscorn surfaces. My exponents here are just 3 numbers. So, such a surface depends on 3 numbers, P, Q, and R. And this is just the 0 set of x power P plus 1 power Q plus Z power R in C3. A lot of things is known about these surfaces, but I would like to discuss only one topic, namely curves. I would like to consider polynomial curves. So this is just a morphism from a line from my C1 to such a surface. If you will think a little which surface, which curves can be constructed on such a surface, then you will immediately produce trivial curves. Namely, just take one polynomial in a corresponding powers with the corresponding coefficients. This is quite easy, so I will write it down. X is some coefficients and some polynomials power m over p. Y, some coefficient, the same polynomial m over q. And z, the same. Where this m is a latest common multiple of EQR, and alpha plus beta plus gamma satisfy our equation. So this is somehow non-interesting trivial curve. And one can ask, when do we have a non-trivial curve? And it turns out that such a non-trivial curve exists. So plane is that my surface admits a non-trivial curve if and only if it is irrational. We have explicit condition for such a surface to be rational. For surface it was known before. And so such a result is available. I cannot put here the exact reference because it was distributed between several papers and it's difficult to connect it with just one. But I have the same result for hypersurface when I consider trinomial hypersurface of this type. And one more claim in this direction, really beautiful, coming from 19th century, is the following one. Definition. Let me say that a triple EQR is Platonic if I have the classical inequality 1 over P plus 1 over Q plus 1 over I is greater than 1. But this is a nice Olympiad problem. In Russia we were like mathematical Olympiads. So it's elementary Olympiad problem to find all such triples, and the answer is the following. This is 5, 3, 2, 4, 3, 2, 3, 3, 2, and 2 infinite series, P, 2, 2, and P, 1. Okay, why do I need such Platonic triples? Next claim let me call it theorem, because this is really classical. It was published first in one direction by Schwarz in 1873. Then other direction was done by Holfen 10 years later. So German and French mathematician. And finally, Russian mathematician Vilmin independently reproved it some years later. So this is 1904. And I was very happy and proud to find this paper in our Math Sbornik, mathematical Sbornik, which is the oldest Russian journal. And the statement is the following. Our surface admits a curve not passing through the origin, through 0, if and only if our tuple is Platonic.
Something is missing.
Something is wrong?
No, missing, because if you want a curve not passing through the origin, you cut this hypersurface, which doesn't contain the origin, right? So
This is just surface case, not
Yes.
hypersurface.
if you want a curve on the surface, it doesn't go to a given point.
Sure.
So,
I certainly mean
some
not trivial curve.
Some word is missing.
Not a point.
Then I'm away from it.
Really curve. The image of this should be not 1 point. these papers, they deal with Diophantine equations, because this is a question about how to solve such a Diophantine equations over their polynomials in one variable. And the condition that our curve does not pass through the origin just means that we are looking for co-prime solution of these equations. And in this paper it was proved that such an equation has a solution to co-prime polynomials if and only if we have this Platonic condition. And explicit, certainly there are infinitely many solutions, but explicit solutions were found by explicit formulas. So it's, and again, I have some quite straightforward generalization of this. Okay, so I have a little bit more than 10 minutes now to explain why trinomials.
So now you are saying that you have some generalization of root systems, yes?
Here?
Yeah.
No.
Okay.
Just some conditions.
These are just root systems. I mean, ADE.
Yes, but I just defined what is a Platonic condition for hypersurface. And this is exactly the same condition for somehow first exponents in this term.
Oh.
So unfortunately no new root system is used in this case. Okay, and now some explanation why are we interested in trinomials, how are they connected with actions of complexity 1. In fact, we already know that such a hypersurface admits an action of complexity 1, but if this is just one example, this is not interesting, but in fact, this is not just one example. All actions of complexity 1 can be obtained by not necessarily one, but from a system of trinomials. And this is what I'm going to explain now. This is about Cox ring. The way to connect actions of complexity 1 to trinomials is to consider Cox ring. So I take some normal variety x. I'm sorry, because time is quite limited, I will omit some technical condition, just explain the general ideas. So the Cox ring associated with this variety is just a graded ring. This ring is graded by classes, by the divisor class group of my variety. And this is the sum of some components. Here I use non-classes but representative of a class. And this is some difficulty for the theory of Cox ring, but nevertheless we do like this. And these components, which looks like spaces or sections of some line bundles, but D may be not Cartier, but just a divisor. These are just some subspaces in the field of rational functions. Namely, the condition is that divisor of f plus d is effective. So this is some nice ring. Certainly it's natural to assume that the divisor class group is finitely generated. Otherwise I have some huge ring, no sense to study. If the divisor class group is finitely generated, then we have such a gradient for a finitely generated group. If variety X is complete, then such homogeneous components are finite dimensional. In general, they can be infinite dimensional. And we have such a theorem, which I will mention 2 papers, 6 and 7, say that if the divisor class group is free, if it is a lattice, then the Cox ring is unique factorization domain. And in general, if it's not free, we always have this graded factoriality. We always have this unique decomposition into primes for homogeneous elements. But UFD we have not always. And I would like to propose you the following example, exercise. Just to feel how, okay?
I have a question. So, do you assume in that theorem that X is a prime or just X is any variety? Here?
X is any variety. I don't like invertible regular functions on S. but these are technical conditions which I want to omit. But now I consider arbitrary variety. And what I want to say now, I even don't want to have a variety. It's work very well for pre-variety. And let me consider the following pre-variety. X is a T1 with several double points. A0, AR. And even not necessarily double points, but points with some multiplicities. And multiplicities I will denote by M. This is just usual P1, but some points are non-separated somehow. So this is not a variety. The coordinates of these bad points, let me denote it by alpha beta. And the divisor class group of such a pre-variety, you can compute it, and this is just lattice of rank sum of n's minus r. And just take this definition of the Cox ring and compute the Cox ring of this object. And it turns out that it's natural to introduce monomials, Ti. So this will be Ti1, Ti, and I. All exponents are 1, so this is a particular case of this. And then the claim is that the Cox ring of such a one-dimensional pre-variety is the quotient of the polynomial rings in this variable modulo some trinomial relations. Namely, here it will be some minors, some determinants, alpha j, alpha k, beta j, beta k, times ti, and the same coefficients for tj and tk. So, this is somehow explanation how trinomials appear for actions of complexity 1, because this is a good candidate for a quotient for a t action. We know that when a torus acts on an arbitrary variety, there always exists a covering by affine t charts. We can take categorical quotient for any affine t chart. It will be something one-dimensional. We will glue it together. So we will always have a quotient, but this may be non-separate. And there is a relation between Cox ring of the quotient and Cox ring of the original variety with the t action. And computing the Cox ring of such a one-dimensional variety, one come to trinomials.
Here R is equal to 2.
Sorry?
R is equal to 2.
Huh?
R plus 1 plus.
Right. And minus r, not minus r plus 1, but minus r.
I'm a little bit confused. What is the relation between I? What is the range for I?
You asked about this, right? No? About r.
So you have 3 R-dimensional.
I have many variables. The number of variables is equal to the sum of these multiplicities. And I have relations of this form. So I have trinomials, where each term is just a product of variables in power 1 and some coefficients. When I have just one relation, then I can forget about coefficients, just rescaling of the variables. But if I have a system of trinomials, then I really do need coefficients. And if you will look closer to these relations, you will see that there are 2 terms, and all other terms are linear combinations of these 2. So these relations are always something like third, fourth, and so on. Terms expressed as a linear combination of first one. Okay, so theorem. Proved in 1 and in 8. In 8, the general, more general version. The following conditions are equivalent. Condition first, I will formulate it in a very informal way. Cox ring. Think, I take some algebra. A. A is a Cox ring of a normal rational variety of complexity 1 with a torus action, this T action of complexity 1. Second condition, A carries a complexity 1 grading which is factorial on the level of homogeneous elements. And finally, the last condition is that the A is a quotient of polynomial algebra by an ideal generated by trinomials. Certainly I should be more careful in defining what are trinomials in general. I will not write it explicitly, but the idea is that we have two trinomials and all other depends on other variables, and they are linear combinations of these two. So this somehow relates trinomials and actions of complexity 1, because it's known that if you know a Cox ring of your variety, you can reconstruct your variety as a categorical quotient of some open subset in this variety. So if you consider a fine variety coming from trinomial, you can in some sense produce all T variety of complexity 1. And historically, the first place in the literature when I found a connection of trinomials and complexity 1 actions was a paper by Panishev in 95.
So what did you want in point 2?
Carries a complexity 1 gradient which is factorial. And in my terms, in these terms which I use in this talk, maybe the first result was by Carlson and this in 0 in 10. Okay, and very last part number 9. This is about homogeneous LMEs. Homogeneous locally important derivation. It was rather interesting to study the geometry of our trinomial hypersurfaces, say study rationality, but there is even more funny thing, is to study homogeneous locally important derivation. So when we take the algebra of regular functions of my variety, which is graded by some finitely generated Abelian group, and you consider derivations, linear maps which satisfy Leibniz rule, and locally important means that for any element it's annihilated by an appropriate power of D, and you assume that this is homogeneous, means that any homogeneous element goes to a homogeneous one, but this is equivalent to the shifting of component. The image of any homogeneous component is contained in another homogeneous component, and the shift doesn't depend on U, so this is some element which I call the degree of this variable, of this derivation. So, just to say some words about this, if you consider the complexity 0 case, so if your gradient is of complexity 0, it means that all homogeneous components are one-dimensional. And then our algebra A is just a semigroup algebra of semigroup of integral points inside of some polyhedral cone. So we have something like this. And then any derivation is defined on the homogeneous elements, and this is just look like some scalar, then some pairing of my weight U with some ray of some cone, and then just some shift of the derivative. Very explicit formula, and this shift E is what is called Demoiselle root of the dual cone in the dual space. And for complexity 1, we also have description of homogeneous derivation, homogeneous elements. It was done in our paper number 9 under some permittivity condition, and now my student Yulia, who is here, and Sergei Gaifulim, they have a general description. I will not certainly give it, but why it is important? Because it allows to describe connected component of automorphism groups of complete varieties, rational complete varieties, with the T-action of complexity 1. So one can describe not connected components, but at least not all components, but the component of unity generated by the acting torus and such root subgroups. And root subgroups, they correspond to homogeneous LMDs. So the toric case is classically known. This is due to Dimazur. And a remarkable result is that when you consider the semi-simple part of the automorphism group of complete toric variety, this is a linear algebraic group, and semi-simple part has type A. So known as a root system. And in complexity 1, what is nice is that we have type 1 plus exactly one new root system, as Nikolai Alexandrovich requested, namely B2. And this is just because of the trinomial x1, x2 plus x3, x4 plus x5 squared. This is a trinomial, and it corresponds to the automorphism group, orthogonal group S of 5, and this is precisely this root system. So something new here for complexity 1. And this is the only good one. We have a complete description of the automorphism group of a complete rational T variety of complexity 1, using this technique of homogeneous LMDs for trinomial algebras. Thank you very much.